Hey there, this is Dr. B, and let's take a look at mass spectrometry. Most scientists use this for one thing and one thing only, and that is to determine the molecular weight, or if you will, the molecular mass of some pure substance. It's interesting educationally, but perhaps less used practically, to use this tool to identify isotopes, but it does so very nicely. Here's the device. Notice that it's now small enough that these can fit on a bench top. They can be perhaps $10,000, whereas I'm sure they were many multiples of that before. And you can still get much more expensive devices. And the way they work is they take a pure sample. Usually there's a carousel. I don't know if I see one there, perhaps up there. And you put your sample in there dissolved in a liquid. The carousel moves it to the platform. It injects a needle into it, pulls up a little bit, and then ionizes the sample. It does that by subjecting it to electrons, where those electrons will rip off an electron, giving you a molecular ion. Now it conducts electricity, and you can do unique things with it. And we can see how heavy that item is by putting it in a magnetic field. It's a little harder to deflect the heavier items. You can calibrate that device. It hits the detector, and the ones that are deflected the most are probably the lightest, and you can get a number from that, and that is molecular ion. Now, I'm sure lifetimes of research have gone into developing these techniques, and the big challenge is that the objects tend to fragment once they ionize. They tend to fall apart. So the trick is to get it to fall apart, but not much. It was originally believed that these fragmentation patterns can be very diagnostic, and I think to a certain degree that's true, but my own work in labs has shown that that's more of a curiosity than anything. The molecular ion's wonderful. There's plenty of other ways to get the rest of the information about the substance. Here is a mass spectrum of caffeine. It has molecular weight of 194, and there you go. There is the ion sample. Sometimes with these nitrogen-containing substance, you'll get the NH plus sample as well. That's probably 195 there. And there's some fragments there, which you can scope out if you want to. That's fine. But it'll end up with molecular weight of 194. This tends to fit that, C8H10N4O2. This would probably come from elemental analysis. So first you get its 194. Then in this particular case, if you did elemental analysis, I think you'd get C4H5N2O1. That would be called its empirical formula. Getting the molecular weight is key to turning that ratio of elements into their true ratio for the molecule, and you'd have to double it. And there's your molecular weight, fine. And then you come up with candidate structures. Now, the problem with mass spectrometry is there's going to be a lot of isomers that can fit this. Oh my God, so many isomers. Most chemists at this point would take what they call an NMR of the sample, which would give them a detailed map and lead to this structure here. But if you had to guess among isomers, you can turn this formula into how many double bonds and or rings it has. It could also be, of course, a triple bond, which is equivalent to 2 double bonds. So sometimes they call this a double bond equivalent analysis or an index of hydrogen deficiency. And here's the formula for it. It's always equal to 0.5 times twice the number of carbons, which here is 8, plus 2, so that would bring it up to 10. Well, 16, whatever. You can do the formula. So it's 2 times the number of carbons plus 2 minus the number of hydrogens, which is 10 here, minus the number of halogens, fluorine, chlorine, bromine, and iodine, which this doesn't have any of, plus the number of nitrogens. If you take that and plug it in, it'll give you the index of hydrogen deficiency. That simply tells you how many double bonds and or rings this must have. A double bond reduces the number of hydrogens by 2, as does a ring. So they call these double bond equivalents. And in this particular case for caffeine, I'm counting 1, 2, 3 double bonds, 2 rings. I believe it has an index of hydrogen deficiency of 6. Let's do it again. 1, 2, 3, 4 double bonds, 2 rings. IHD, I believe, would be 6. It seems like an obscure thing to do, but it can really narrow down the possible isomers if you know what you're looking at. Like if you had C6H6, this is one way to draw it. It has an index of hydrogen deficiency of 4. See, it has 3 double bonds in a ring. Similarly, This chlorofuran molecule would have an IHD of 1, 2, 3. So anything that you draw that has, let's say, 3 double bonds or 2 double bonds in a ring, or 1 double bond and 2 rings, or no double bonds and 3 rings, all those would match that molecular formula, which is just a handy thing to do. So that's index of hydrogen deficiency. Mass spectrometry can also reveal isotopes, and from an educational point of view, this is where most of the questions typically come from. The zirconium mass spectrum, for example, is not just one big peak of one zirconium atom, but rather each atom may have different molecular weights. That meaning that, isn't that unusual? They're all pure zirconium, but look at this, it goes from 90 to 96. The reason? Well, they're all zirconium. They all have the same number of protons, but the number of neutrons does vary. And the mass spectrum shows you the ratio in which they vary. This leads to what we call average atomic mass, a very useful number, since for even a handful of zirconium you're going to have so many zillion atoms that that average mass will be matched pretty much exactly. How do we calculate it? Well, we just turn these into percents and get an exact mass for each of these. And here it is. The mass for zirconium-90 is actually 89.905. That's 51% of your sample. Zirconium-91 is 11%. And all you have to do is add them up, multiplying them by their abundances. Abundances means turn your percents into decimals. That means take 100th of each one. So here it is. 51% roughly of your sample checks in at 89.9, 11.22 checks in at 90, and 17 at 91.9. That's right there. Sometimes people write 0.280 here, but remember to take 100th of it. 2.8% of the sample is 95.908. Punch it all in and you'll find an average atomic mass of 91.224 AMUs. That should match what you see on the periodic table. This is an introduction to mass spectrometry.